2.
Minus 2 is going to be 2.
Negative 1.
And am I writing this?
No, 1 times 0.
1 times 0. So 0 minus 1 is minus 1. Okay? So this is going to be the vector we're looking for. We have a point, we have a vector, so we're vector. So RT is equal to minus 3 plus 0t, so it's just minus 3. Then 4 plus 2t, and 2 minus t. Okay? This is the equation of the line we're looking for. Okay? So, to summarize, we might have different kinds of conditions, but in the end, there are two things we need to figure out: a point and a direction. How to find the point, how to find the direction, that's according to the condition. Okay? Okay, so in terms of the helix I'm talking about, the only thing I want you to be able to do is to recognize what helix is and try to determine its axis. So here is the helix. RT is equal to cosine t, sine t, and t. Okay. For simplicity, let's just say my t is all the real numbers, so there's no restriction at all. Okay. So one important remark I want to make before this, before I try to draw my version of the helix, I have to make one warning: is I am terrible at drawing. See, if you look at my personal before, I don't draw very nice pictures on board. But because this is kind of a three-first, I have to practice my drawing skills together. We're going to practice our drawing skills together. Okay? So I will try to draw this helix here. But the remark I want to make is we begin from the straight line. We begin from the straight line because this is a pretty straightforward computation. As long as you have a point, you have a direction, you know where this line is and where this line is going. Right? For any other general vector value functions, in order to draw the curve corresponding to the function, the unique way is to plot the points. Everything? For a straight line, we didn't really plot the points because it is too simple to do that. It's just line. As long as you know the direction, it's pretty much fixed. But for any other vector value functions, as long as we want to draw the corresponding curve, I need to plot points by choosing my t values, and then I need to find my x value, my y value, and my z value. Alright? And then for given different values of t, I have different points on the space. And then, as long as I have enough points on the space, I line them together smoothly, I'm getting the curve corresponding to the vector value function. This plotting points way is going to be the uniform way for every given vector value function. It's only because we're looking at a straight line first that we didn't do that. It's just too simple. But for any other vector value functions, we should begin from choosing special values of t and x, y, z's in order to locate those points. Okay? Are you with me? So we're going to do this for helix. So what points do you want to choose for, what values do you want to choose for t? The bottom line is I want these guys to be easy to compute.
0,
right? 0, so x is going to be 1, 0, and 0. Okay? So hopefully I can do a good job here. So x, y, z, the first point is on x-axis, so this is the 1. Okay? What's next I want to choose? Pi half. If t is equal to pi half, s is On the other direction, if you are looking at this helix from above, from the positive direction of the axis, you squeeze everything back onto the xy plane, it's going to be nothing but a unit circle. Okay? So this is basically, you have the unit circle, and then along the z-axis, you're stretching the unit circle to get a spring. Okay? So if you can imagine, hopefully that will give you some hint. So when t is increasing, z keeps increasing. So z is the axis that is stretching out the unit circle to get a spring. Okay? I apologize for my drawing skills. So this is going to be the best effort for my helix. Hopefully yours will be better than mine. And also there's a very nice picture on the textbook. Okay? So I'm sorry I'm disappointed again. Because I want to do another helix with different axes. So there are two things I want you to be able to recognize with the helix. First is the axis. The axis is where it doesn't contain cosine or sine. So in the z direction, it is the direction where you're stretching out the unit circle. So this is going to be the axis. So along the axis, if you squeeze everything along the axis, it's going to give you a unit circle for x and y. Are you with me? So that's the two things I want you to be recognized, and that's it. So if generally I have a vector value function given by, say, ct, a cosine t, b sine t, I can also easily tell the axis is going to be the x-axis, okay? Because this is the direction where it's stretching out, okay? So the x is the axis. Axis is the axis of the helix. And along this axis, if I squeeze everything back onto the y-z plane, I'm going to get the ellipse as we discussed before. know the differentiation of the function. For instance, with respect to the independent variable x, I have a so-called partial derivative. If I know the partial derivative is equal to 2, back onto the graph, what does this 2 tell me? Okay, so the differentiation as well as the integration are some information you can tell from the graph. So that's the motivation why we want to study this graph in the very beginning, so that when we introduce the differentiation, taking derivatives, we will know back onto the geometric stuff, what is this computation trying to tell us. Okay, so still the easiest surface is going to be a plane. All right, the easiest curve is a straight line. The easiest surface is a plane. Let us have this fact straight. A curve is a one-dimensional object. All right, a curve is a one-dimensional object. In terms of you only need one variable to change in order to get a curve. A plane is a two-dimensional object. Okay, essentially you need two parameters to vary in order to get a plane. You need to go this direction, you need to go that direction, and then you will span the whole plane. So a plane is a two-dimensional object. Okay, straight line, circle, ellipse, they are curves. If you have a sphere, if you are talking about sphere, these are surfaces. They are two-dimensional objects. Okay, are with me? So in the very beginning, let us get this fact very straight. And next, I want to get the equation of a plane. Let me ask you this question. If I want you to fix a plane, remember, I asked you this question to fix a line. You need a point and a direction. If I want you to describe mathematically what a plane is, how do you say that? How do you tell people you are describing a plane? You need a point on the plane, okay?
Normal line.
A normal line. A normal line, how do you use the normal line? How do you use the normal line? In other words, what do we mean by normal line? So you have a normal right here, you have a point which is on a plane. A normal line is talking about any other line containing in this plane will be orthogonal to the normal line, right? In other words, any point containing on the plane, if you line this with the fixed point we have in the very beginning, this segment will be orthogonal to the normal line, right? Think about this. A lot of easy concepts in real life are not so easy to describe strictly in a mathematical term. If you want to fix a plane, you need a point, and you need a direction. But this direction is not going to be the direction of a line going to that direction. A line is a one-dimensional object. In the two-dimensional object, we need a normal